Hi class. So for this project in class, I'm asking you to do measurements that will empirically demonstrate the relationship between the volumetric flow rate and the length of pipe and the volumetric flow length and the diameter of the pipe for pressure-driven flow. I've given you an equation where that the pressure gradient is going to be equal to a whole mishmash of constants, times the average fluid velocity, and it's proportional to length and inversely proportional to diameter by some factor, which you're going to calculate using your plots, or you're going to determine using your plots. And notice that here I have y prime. Y is not equal to y prime because u is not equal to q, but you can convert between these as explicitly determined by the geometry of your setup. So as you might imagine, all of these relationships are influenced by all sorts of things in the experiment. The L and D are called out explicitly, but we should maybe expect that some material properties of our fluid are hidden in here, as well as some material properties of the pipe. And that's true, and now today this little video is about illuminating a little bit what sits within this mishmash of constants. And I'll point out again that that's fundamentally different from the empirically derived equation PV equals nRT, where R is a universal constant. It comes to us from something about the universe, and it's invariant regardless of the material that you're thinking about or talking about. There are no material properties in this equation. Okay, so for flow, here's data that was taken for 21 experiments, actually using probably some of the apparatus that you have in class, but fitted with flow meters and pressure meters. And it was actually done by CAs for transport about 7 years ago. So this figure is in Brian Story's textbook, and a number of the figures I'll show you today are in Brian's scattered throughout his book, and you can find that book on our Canvas site, in the files on our Canvas site. So you'll see that velocity as a function, we can see the change of velocity as a function of pressure for all of these different experiments, and these different experiments varied in the type of fluid that was used, and also the geometry of the system, the length of the pipe and the diameter of the pipe. Okay, I've pointed to the idea that humans have three ways of discovering equations that help us understand physical phenomena. We can a priori derive equations, we can empirically discover them, and there's this middle ground, which is using deep physical intuition and mathematical tools called dimensional analysis. One thing that comes out of dimensional analysis and the procedures that are done in this technique is useful groupings of parameters. So instead of plotting velocity versus pressure, if I choose instead to plot this quantity here, which is kind of it's like a dimensionless pressure divided by the length, so it's a little bit like a dimensionless pressure gradient, versus this grouping of constants, all of these data collapse to a single master curve. And now we can really see there's some physical phenomena here that are illuminated. And using this curve, then you can see that there are two different flow regimes. Two things are changing. Both the slope is changing and the variability of the data is changing. So this grouping of constants is rather famous. It's called the Reynolds number. Notice that this u is the fluid velocity, this is the Greek letter mu, and this is viscosity. The rho is the density of the fluid. You'll see in fluid experiments that there are often regimes, two different regimes. And this low Reynolds number regime corresponds to laminar flow, and this high number Reynolds number regime corresponds to turbulent flow. What the Reynolds number is, you can see based in how this equation is written, is basically it's a ratio of inertial forces to viscous forces in a fluid. Okay, and at low Reynolds number, the flow is laminar and viscous forces are dominant. At high Reynolds number, the flow is turbulent and inertial forces dominate. Jillian, our writing specialist, would point out that I used 2 different parts of speech to write that out. Whoopsie doodle. Okay, so let's go back to our equation. Oh, actually, no, sorry, I'm going to pause. I want to show you what this transition looks like experimentally, or visually. So what we have here is these are 3 different pipes with fluid flowing through the pipe under pressure-driven flow and a dye injected. So here's the dye for the top pipe, here's the dye for the middle pipe, and here's the dye for the lower pipe. And this top pipe is demonstrating laminar flow, where viscous forces are dominant. You can see the dye stays tidy, nice down the center. And then turbulent flow in the bottom with the transition regime in between. So what we're seeing is a nice visual depiction of like how fundamentally the characteristic of flow changes as a function of this Reynolds number. Okay, but let's go back to the equation from class. Delta P equals this mishmash of constants, average velocity squared, times some relationship of length over diameter. I'm now going to name this mishmash of constants. I'm going to give it a name. I'm going to call it the friction factor. Based on what I just showed you, I hope you have an idea or some imagination that this friction factor probably depends on the Reynolds number. So let's see what it looks like to plot this friction factor as a function of the Reynolds number. So here's that data here. Again, you'll see that our experiment breaks into 2 different flow regimes. These low Reynolds number flows are laminar, these high Reynolds numbers flows are turbulent, and there's a transition region in between. At low Reynolds numbers, this friction factor, it appears quite linear with Reynolds number, and in fact, in this regime, the friction factor is only dependent on the Reynolds number and is equal to 64 divided by the Reynolds number. In this higher Reynolds number regime, the friction factor gets more complicated. Here, the friction factor is actually going to be dependent on not only the Reynolds number, but also some characteristics of the pipe. It'll be important. It'll depend on a parameter that is something like the pipe roughness relative to the pipe diameter. I think based on what I saw in the parts that you're ordering, in this class, some groups are going to collect data that span. We'll have data from the class that span both of these regimes. And so when you're thinking about how you analyze your data, it'd be good to be aware that you might switch regimes. At this point, I think you have what you need to describe the data that you collect, but I'm going to show you 2 more things that are just general fluid dynamics, for just your general fluid dynamics edification. Okay, one, if I plot, this experimental data is for 1 tubing type. So if I plot, do this experiment, friction factor versus Reynolds number for a whole bunch of pipe materials, That diagram, that data is classically called Moody diagram, and what I have here are a whole bunch of different pipes. And on this y-axis, the pipes are the data is organized according to relative pipe roughness. So you can use these tables to go, if you don't have experimental data but you want to do a simulation, you might use the Moody diagram to go look up what the friction factor of your system might be under the conditions you're interested in simulating or calculating. Okay. The second thing to tell you is that you might encounter the term Poiseuille flow, but it's not, it's spelled like this. So Poiseuille flow is mathematical tools that were developed to describe laminar flow. If you can pronounce this as Poiseuille in an interview, then you have a leg up. But also, this is probably the term you want to Google if you want to see more math that describes the laminar flow regime.